Hello, I'm Micah Willoughby. This is JW. This right here is Luis Flores-Moreno, and we are Group 8, and our project is Variable Refrigerant Flow Systems. Variable Refrigerant Flow is a system that is advanced and energy efficient, and it's designed to precisely regulate refrigerant flow to individual indoor units. This is good for buildings like schools or hotels where there are multiple zones and each zone requires a different temperature control. The operating modes are heat pumps and heat recovery systems. And the heat recovery systems takes one excess waste from one zone and uses it for another, making it a very efficient way to heat or cool the building. Basically, the overview of this system is a single outdoor unit that is the compressor that um, it compresses the refrigerant and sends it through the lines to each individual indoor unit where a fan coil is there, and depending on the load that each unit needs, it adjusts the refrigerant going through the fan coil to basically change the temperature of the air that is going through the system.
Comfort through precise control. Traditional HVAC systems cycle compressors on and off, causing temperature fluctuation. In contrast, VRF systems run continuously, adjusting compressor speed to maintain steady indoor temperatures. This precise control improves comfort and extends equipment life. Fan speeds and lower position at each indoor unit can also be adjusted for personal comfort. Here to the right, we got Figure 10, which is a typical VRF heat recovery system with simultaneous heating and cooling operation. Fan cooling and zoning flexibility. VRF systems support a wide variety of indoor unit types, including wall-mounted, cassette, and ducted models. This flexibility allows system design to align with the size, shape, and function of each space. Proper unit selection prevents mismatch between capacity and load, reducing the risk of inefficiency, overuse, and premature equipment failure. Here we have a zoning layout for VRF system. Simplified and cheaper installation. VRF systems eliminate the need for ductwork, simplifying layout design and preventing energy losses through air distribution. They also reduce reliance on pumps, boilers, and large piping typically required in chilled water systems. Outdoor units are compact and lightweight, small enough to fit in elevators, avoiding the need for cranes. Lower raw tube loading minimizes structural reinforcement, cutting down on overall installation costs. Here for Figure 2, we have the traditional fixed speed compressor operation. Efficiency and performance. VRF systems deliver conditioned air directly to individual zones, minimizing thermal losses. Twin rotary compressors outperform scroll types by maintaining high efficiency across a wide speed range. Reduced pole circulation enhances metering precision and system control. With energy usage scaling to match demand, VRF systems excel in part load conditions, maximizing performance and saving. Here for Figure 2, we have a VRF system inverter-driven compressor operation.
So some things that you need to take into design when you're looking at installing a VRF system or just any HVAC system in general is your building orientation and exposure. So, you need to look at how the building's situated. If your sunny side of the building might need a little bit more cooling in the summer because it's getting the full sunlight than the other side of the building. You also need to look at the seasonal demands for heating and cooling. Also, the zoning layout and the space usage, that's where you can really see some of the benefits of VRF, and it can really save you some money is when you have a lot of different space loading demands. So in a lot of different rooms if they're hot and cold. And then based on your analysis of the building and how it's going to be laid out, you can choose from either a VRF heat pump system or a heat recovery system, which can do simultaneous heating and cooling at the same time, which can really save you some money. And also you need to consider the piping configuration, because VRF has a lot of pipes, and unit sizing, and just your total refrigerant volume, because you got to stay within the ASHRAE standards. So one example you can think about in this scenario, consider just an office building with 6 different zones, and they each have different heating and cooling requirements. So the boss man likes his office very cold, but the other person does not. So with VRF, you can group the zones that have a similar profile. So if all the rooms are under a similar temperature and they're kind of being loaded a similar way, you can pipe all of those to a single outdoor unit. So you can save some electricity that way. And you can simultaneously cool one zone while heating another. And this can optimize energy usage, and it maintains comfort across all areas so that the people can be comfortable no matter which space they're in. And this capability makes the variable refrigerant flow ideal for buildings with varied occupancy and usage patterns as well, because you can turn it off when there's not as many people there. We did a HAP study for this report. I put in 3 different buildings. I did an office space, smaller office space, a hotel, and a factory, just to kind of compare the variable refrigerant flow to a VAV system, which is a rooftop, a traditional HVAC unit. Yeah, I just use that kind of as a baseline. But anyway, it came out for the office building, VRF was cheaper than the traditional units because it was extremely cheaper to cool, and it had a lower fan cost as well. It took less electricity to run the fan, but a much higher heating cost. But overall, it was cheaper to use VRF for the office building. Now, the hotel had cheaper cooling in VRF, but overall, VRF was much more expensive for the hotel. And I think that's because it wasn't set up correctly. I wasn't able to get all the different rooms implemented into that building. So that alternative, I think, was a little bit flawed. In real life studies, they've studied real hotels, and VRF does save money, and it is less energy intensive for hotels. So, and then in the factory, which is just a large building, the VRF was more expensive because of the extra pipes and extra installation costs, because it's not as efficient in large warehouses like that. So in conclusion, VRF is a modern modular HVAC solution designed for efficiency and flexibility. You can use it in many different situations, and if you use it in the right situation, it can deliver significant energy savings, precise comfort at the zones, and it also, in some cases, is cheaper to install and operate. So with its scalability and zoning capabilities, VRF is ideal for multi-use facilities like schools, offices, and hotels, where adaptable climate control is essential. So overall, this was an interesting study to do.